Hello everyone. This is the fourth worksheet on hypothesis tests, and this one is on hypothesis test for one population mean when sigma is known. All right, sigma is the population standard deviation. So when the population standard deviation is given to us, or we know it is known, then we follow the Z test procedure to perform a hypothesis test. All right. Now here we will perform a hypothesis test from scratch, from the start, by stating the null and alternate hypothesis. Then we'll have to figure out what kind of test this is, and then we will have to use one of the two approaches, the critical value or and the p-value. Actually, not one of the two, but both these approaches. And before that, we will also be doing the calculation of our test statistic, and then we will take a decision based on what we find from these two approaches, and then at the end we interpret our hypothesis test. Okay, so let's look at the first problem. It says here we have provided a sample mean, sample size, and population standard deviation. So they have given us the population standard deviation, and when that is known, when sigma is known, then we can use the Z interval, not the Z interval, but the Z test procedure for hypothesis testing. Now in each case, use the one mean Z test to perform the required hypothesis test at the 5% significance level. Now, this is not really an application-based problem. This is just a straightforward problem where they have given us the different data points, and they've also kind of stated the hypothesis for us. So all they want us to do is to use this data and perform a complete hypothesis test. Okay, so what is the data they've given us? They've given us X bar, which is the sample mean, is 20, and then N equals 32, which is the sample size. Sigma, the population standard deviation, is 4, and the null hypothesis states mu equals 22. The alternate hypothesis claims that mu is less than 22. And the first step in any hypothesis test is to state the null and alternate hypothesis. Since this is a straightforward problem and they have stated the null and alternate hypothesis for us, I'm just going to write them out as is. So null will be, you have to write it out as H sub O. So null hypothesis colon mu equals 22, right? So whatever is given here, just write it for the null hypothesis. Now for an application-based problem, it's not going to be as straightforward and simple as this. You will have to figure out what the null hypothesis is and what the alternate hypothesis is. But since we are just starting off with the first problem, let's just use whatever they have given us, and they've kind of made it simple for us to start with. All right, so the alternate hypothesis says mu less than 22. Determine the type of test. Now, for the type of test, there can be two types. All right, one is the Z test. So first of all, it's a Z test because we are given the population standard deviation. So therefore, we are going to use the Z test procedure. All right. However, what they are asking here is the tail type. That means, what tail test is this? Now, so let me write that here, tail type. Okay, now what kind of tail type it's going to be will be determined from the alternate hypothesis statement. If the alternate hypothesis has a less than in its statement, all right, it has a less than in its statement, then it's going to be a left tail test. It's going to be a left tail test. That means the reject region is going to be to the left of our normal curve. That's what it means. Part C says determine the significance level alpha you are testing at. Now, what alpha value we will be using will come from this 5% significance level. Now, alpha is the decimal form of this 5%. So I'm going to write it as alpha equals 0.05, right? Part D says draw a diagram showing rejection and non-rejection regions based on alpha. Okay, so let's see. We have to draw a figure here, which is a normal curve, right? So let's draw a normal curve. And based on the information we have been given so far, all right, the null hypothesis mean is going to be located somewhere in the center, and the null hypothesis mean will have a z value of 0, all right? Now, it also says, all right, that it is going to be a left tail test. So I'm going to put my reject region to the left. So in a left tail test, the reject region will always be to the left. And we also know that the area associated with the reject region, all right, the area under the curve associated with the reject region is the alpha value, the significance level alpha value, which is 0.05. All right, so we have to find, when we use the critical value approach, we will have to find the cutoff between the reject and the do not reject region, correct? And that value will be negative z of 0.05. It's going to be a z value because we are using the z test procedure, and it's going to, the alpha value associated with that z is 0.05, which comes from the significance level. And because it's located to the left of 0, it's going to be a negative z value. All right. So that's the diagram showing the rejection and non-rejection regions are based on the alpha, and this is applicable to the critical value approach. All right, the reject and do not, all these regions, reject region and do not reject regions, correspond to the critical value approach, not really the p-value approach. All right. Now, part E says calculate the test statistics. So this is what our evidence is going to be, and this test statistics will be obtained from our sample data. Okay, so our sample data here, which is x bar and the value of sigma, all right, these are our sample data values, and we will be using those to come up with a test statistic. The test statistic in this case is a z value, and the formula for the z value for this hypothesis test is going to be z equals, all right, z equals x bar minus mu over sigma divided by square root over n. Now you will find this formula in your formula sheets under the chapter for hypothesis tests. So you can look that up, all right, from your formula sheet. But let's plug in the value and find the value for z. Okay, so x bar is 20, right? X bar is 20 here. And then this mu is the null hypothesis mu. It is the null hypothesis mean. So minus 22, and then sigma is 4. All right, the sigma, population standard deviation, is given as 4. So 4 divided by n is 32. So square root over 32. All right, so it's 20 minus 22 is negative 2 divided by, now 4 divided by square root over 32. Again, you can use your calculators, but it's going to be 0.707. And when you do this calculation, you should get a value of negative 2.82. So the test statistic value, which is often written as z sub 0, is, all right, is a value of negative 2.82. So let me just highlight it, right? It's 2.82. Now, in the next step, we have to perform the test by these approaches. All right, again, you know what? I'm going to probably remove the highlight because for the time being, because it's kind of hiding the value there. Okay, so for the critical value, we have to first find what the critical value is, but always start off with a diagram. And the critical value diagram is going to be whatever we drew here, but I'm going to repeat the drawing one more time. Okay, so here we have our normal curve. Our normal curve. Again, because it's a left tail test, our reject region is going to be, it's the same diagram as we drew here. This is just for an extra practice. We have, you know, a separate part for you to come up with a diagram. All right, but whenever you're working on the critical value approach, you must have a diagram associated with it. All right, so the other area is do not reject. It's the do not reject region. The reject region has an alpha value, the area under the curve here. It has an alpha value of 0.05. And therefore, the cutoff, which is also the critical value, is negative z of 0.05. Negative z of 0.05. Okay. Now, we have to look up our table, or you, of course, you can use your calculators, but you can also look up your table if you do not have a graphing calculator. You will need a graphing calculator to work on this because they come with the statistical package. All right, but graphing calculators are not mandatory for this course, so you will be provided a table with all your tests. Okay, so let's pull up our table here. Oh, did I lose my table? Just a second. Let me pull that up. I'm going to okay, you can use the Z table here. Again, this is the table that the statistics 2 students will be using, but we have a truncated table with special values, special Z values, which we have used before when we were working on confidence intervals. You can use the same table for hypothesis test as well. So Z of 0.05 is 1.645. Right, so because it's on the left hand side, it's going to be a negative, it's going to be negative 1.645, correct? So our critical value, the CV, critical value, is the value associated with negative z of 0.05, which is equal to negative 1.645. Now what we do is we take our test statistic, which represents our evidence, and we see in which region the test statistic falls. All right, whether it falls in the reject region or whether it falls in the do not reject region, and based on that we will take our decision. So negative 2.82 on this diagram is going to be located way to the left of the cutoff, correct? The cutoff was negative 1.645. Negative 2.82 is less than negative 1.645, so it's going to be located left of this value here of our cutoff. Let me write that. It's negative 2.82. All right. So it falls on the in the reject region, correct? The test statistic value falls in the reject region. So the way we are going to write this is z sub 0 of negative 2.82 is less than negative 1.645. It falls in the reject region. So our decision is going to be reject the null hypothesis. Reject the null hypothesis. Now, it is important that you write for the critical value approach that your test statistic falls in the reject region, that your whatever value you have for your test statistic falls in the reject region. That has to be stated. All right. Otherwise, you will not be awarded the full points, the full credit for this question. Okay. So just make sure that when you're using the critical value approach, you also state there that that value falls in the reject region. Now for the p-value approach, we start with the test statistic. So our test statistic value is z sub 0 equals negative 2.82, right? Now we have to find the area corresponding to this test statistic z value. In other words, all right, here's our curve. Okay, now there's no reject or do not reject region for the p-value approach like we have for the CV approach. However, you still have to draw a figure showing the alpha area, all right, the p-value on the curve, all right? So remember, this is a left tail test, okay? It's a left tail test. Therefore, negative 2.82 is located to the extreme left somewhere here, all right? Somewhere way to the left of the center point, all right? And because it's a left tail test, we have to find the area corresponding to a z value of negative 2.82, all right? So it's going to be the area to the left. This is our p-value, okay? So you have to use your calculators or your table to find the corresponding area, all right? So let me write that here. What we do is we find the area to the left, and to the left just because it's a left tail test. If it was a right tail test, it would be the area to the right, okay? So find the area to the left of z sub 0 equals negative 2.82. Right? So we have to go to our table again. But this time we have to go to our full-blown table here, okay, of the Z table. We cannot use that truncated short table. So negative 2.82. So let's look at the negative Z table, which is this one on the left-hand side. Negative 2.8 is right here. Okay, so I'll use this pen actually. Negative 2.8 is here. And 2.82, correct? So negative 2.82 is 0.0024. Okay, 0.0024 is the area. So let's go back to our worksheet. So this p-value area over here is 0.0024. 0.0024. That's the area. So, and that's the p-value. So the p-value is 0.0024. So that the first step was to find the area corresponding to the test statistic value. And then the second part of the p-value approach is compare p with alpha. All right. So our p-value is 0.0024, and we have to determine, is the p-value less than the alpha value? The alpha value we were given was 0.05. So is p less than, all right, I better write it here, is p less than alpha? Because if it's less than alpha, we reject the null hypothesis. If it isn't, then we will we won't reject the null hypothesis. All right. So it's true that 0.0024 is less than 0.05. So it's true. Therefore, reject null hypothesis. Now, with both your approaches, you should come to the same decision. If you see that with one approach, with the critical value, you have reject, and with p-value, somehow you're coming up with do not reject, then something is wrong somewhere. You have to go and check your work again. All right. So reject the null hypothesis is the decision. Finally, a very important part of this problem, which will carry considerable points, is the interpretation. The way you interpret the hypothesis test is to be written like this. At the, all right, sorry. Let me rewrite this. Okay. At the 5% significance level, you have to qualify your interpretation. All right, that the criteria you used to perform this hypothesis test was at the 5% significance level, because if you used a different percentage, your decision could be completely different. All right, so it's very important that you qualify. So start off saying at the 5% significance level, the data provide, okay, data is plural. So I'm going to say the data provide sufficient evidence to conclude that now, after that, you're going to just write what the alternate hypothesis is stating. All right, to conclude that the population mean, now it's always in terms of the population, because hypothesis test is an inference on the population, that the population mean is greater than, no, it wasn't greater, it was less than, right? I'm sorry, I apologize. So it is less than 22. Okay, so these are some critical phrases that must be included in the interpretation, and there are points associated with those phrases. All right, 5% significance level, make sure you have that. Then the data provides sufficient evidence. All right, now if it is reject, if the decision was reject, then you say the data provides sufficient evidence. If your decision was do not reject, then you will say the data do not provide sufficient evidence. Okay, I'm going to use the data do provide. Right? To conclude that the population mean is less than 22. So if it is an application-based problem, an example of which we will work on later, you will have to interpret it in context of the problem. Because this was a straightforward problem, it's not application based, we will just use the alternate hypothesis statement and say that the data do provide sufficient evidence to conclude that the population mean is less than 22, which was what the alternate hypothesis was trying to claim. All right. Now I'm going to skip solving question number 2 because I'm going to have you work on it by yourselves based on the previous problem, question number 1. The only difference here is that in question number 1, it was a left tail test. Over here for question number 2, it's a right tail test because the alternate hypothesis has a greater than symbol. All right. So I'm going to go straight to question number 3, which will be a two-tail test. And after number 3, there is question number 4, which is actually an application-based word problem, which is also going to be a right tail test. All right. So I will demonstrate the right tail test for a later problem in case you're not sure how to work on the right tail test. All right. But at least try number 2 by yourselves. Question number 3 here states x bar equals 23, n equals 24, sigma equals 4. The null hypothesis statement is mu equals 22, and the alternate hypothesis says mu is not equal to 22, right? So the first step is always to state the null and alternate hypothesis. So let's write that down. Okay, as is h sub 0 colon mu equals 22, and alternate hypothesis is h sub a colon mu not equal to 22. Part B says determine the type of test. It is a z-test procedure, of course, because the population standard deviation is known. However, what they're asking for really is the tail type of the test, which is a two-tail test. Why is it a two-tail test? Because the alternate hypothesis has a not equal to symbol in it. Part C, determine the significance level alpha you're testing at. We are going to use the same significance level because part 3 is a part of the same problem. All right. So we are testing at alpha equals the decimal version of 5%. Therefore, it's 0.05. Okay. Draw a diagram. Now, this diagram is going to have a reject region on both ends of the curve because it's a two-tail test. Let me try to draw a better, little more symmetrical curve. Okay. So because it's a two-tail test has reject regions on both ends of the curve. So it's going to look like this. We are going to have two cutoff points, one reject region to the left, the other reject region just a second, the other reject region to the right, and in between there's going to be a do not reject region. Again, the areas, however, all right, the areas of both the reject region will not just be 0.05, that's the value of alpha. For a two-tailed test, we must divide alpha into two equal parts and distribute it to both the reject regions, all right? So we have a two-tailed test. Let me write that down here. For a two-tailed test, must divide, all right? So must divide alpha by 2. Okay, so we are going to have alpha by 2, which is 0.05 by 2, which is 0.025. So each of these areas of the reject region on each side is going to be 0.025, and it's going to be alpha by 2 rather than the alpha value we are using. And our cutoff values are going to be negative z of alpha by 2, which is 0.025, and positive z of 0.025, all right, on the right-hand side. Part E says calculate the test statistic. So it's the same formula because it is a z test procedure we are using. So it's going to be x bar minus mu over sigma divided by square root over n. It's always a good idea to have the formula in front of you. Then you can correctly plug in the values, all right? So x bar given to us is 23 minus mu is whatever the hypothesis, null hypothesis mean is. So that's 22 divided by sigma. What is sigma? Is it still 4? Yes, 4 divided by square root over 24. So n this time is 24. 4 divided by square root over 24. So we would have a value of 1 divided by 4 over square root over 24, which is going to give us a value of 0. It's actually 1 divided by 0.816, which is equal to 1.225. It's a positive value. 0.816. Okay, so our z sub 0, which represents the test statistic, is 1.225. All right. Now it says part F, perform the test by critical value approach and p-value approach. So again, please draw your diagram. All of these approaches must be accompanied with a diagram, must be supported by a diagram. So critical value approach, again, same diagram as what we drew for part D. I'm going to have my reject regions on both ends. Reject, reject, and do not reject at the center. All right. And then each of these areas, right, this area and this area will be alpha by 2. So it's going to be, this area is 0.025 alpha by 2, and the area to the right, the reject region area, is also 0.025. So we will have a negative z of 0.025 and a positive z of 0.025, okay, on the right hand side. Now we have to go to our table. So let me see if I can pull up the table now. Okay, and we can go to our, just a second. So we use the short table for the special z values, and z of 0.025 is 1.960. So that's going to be the value on the right hand side cutoff. So 1.960, and on the left hand side it's going to be the same value with a negative sign, so negative 1.960, right? So the critical value, you have to write it out though, all right? So critical value is plus minus z of 0.025, which comes to plus minus 1.960. All right, so now we bring our test statistic value z sub 0 and see where it falls in our diagram. So 1.225 is a value between negative 1.960 and positive 1.960, correct? So it would fall somewhere, if this is our 0, then it would fall somewhere here maybe, which is in the do not reject region. All right, but the way you're going to write this out and explain how you come to your decision, you have to say here that z sub 0, all right, the test statistic value z sub 0 of 1.225, all right, is a value between, you can write it in the mathematical way and write it as negative 1.960 less than what was it, 1.225. Here is 1.225 less than 1.225 less than 1.960. All right, you can state it like that also, but you do have to say that this falls, okay, so 1.225 or the test statistic value falls in do not reject region, therefore do not reject null hypothesis. Do not reject the null hypothesis. So that's going to be our decision. However, we also have to work it using the p-value approach. Do not reject null hypothesis. Now with the p-value approach, we start with our test statistic value. So what we do is we find area corresponding to the z sub 0 value of 1.225. Now because this is a two-tailed test, so we want to write that up front here, two-tailed test, because it's a two-tailed test, p-value, right, p-value will be area on both ends. All right, so I'm going to draw a figure here. So we have our p-value, our z sub 0 value, our test statistic value, located somewhere here, 1.225. 1.225 is, let's say, located here. We have to find this area to the right, but we will need to multiply that by 2, all right, because negative 1.225, all right, negative 1.225 will also have an area to its left, all right. This is a two-tailed test. So if we look up our table, all right, let's go to our table again. Our Z table, negative, it was positive 1.225. So we have 1.2 and 1.225. 1.2. You know what I'm going to do is I'm going to look up the negative first. It'll be easier because this table gives us area to the left. So it's better to find the area to the left and multiply it by 2. All right, because that's a symmetrical diagram, a symmetrical curve. Therefore, the area on the left-hand side will equal the area on the right-hand side. So negative 1.22 is 1.22 is negative 1.111. All right, negative 1.112 here to the fourth place. But we have to multiply that by 2. So let me go back here. What it's saying is this area is 0.111, right? Now, this area on the right-hand side is also 0.111, okay? They have the same area. Why did I look up negative 1.225 in my table? Because that table gives area to the left. You could have found the right-hand side area, but you had to do that extra step of subtracting the value you got from the table. You had to subtract that value from 1. Let me just quickly show you what I mean by it. We could have found 1.22, all right, this 0.888. We would just have to subtract it from 1 because this table only gives area to the left. And if we used 1.225, all right, then we would have to subtract that value from 1. All right, so it was most strategically easier to find negative 1.225, find its area on the left, and then just use that as the area to the right. Okay, but because it's a two-tailed test, we will have to multiply it by 2. So p-value is 2 times 0.111, all right, and which is 0.222, all right. So that was the first step. In the second step, all right, we compare p with alpha, right? Compare p with alpha. So the question is p less than alpha? Is 0.222 less than 0.05? No, right? It's not equal to, not less than 0.05. It's false. Okay, so therefore, what do we do if it is 0.222 is greater than 0.05? It's not less than 0.05. when P is greater than alpha, then we do not reject null hypothesis. Do not reject null hypothesis. So yes, our decisions by both the approaches are the same. Interpretation, start off by qualifying the test using the significance level. So at the 5% significance level, the data do not provide, all right? So the data do not provide, oops, sorry about that. The data do not provide. So when it is a do not reject decision, you have to say the data do not provide sufficient evidence to conclude whatever the alternate hypothesis was stating, to conclude that mu, all right, that the population mean is not equal to 20, was it 22? Or was it something else? 22, yes. Not equal to 22. All right. So this is how you work a two-tailed hypothesis test. All right. You have to remember to split your alpha first into two equal parts and distribute it on as the area of the reject region on both ends. For the critical value approach, for the p-value approach, you have to make sure that you multiply your the p that you find from your table or from your calculator, you multiply it by 2, right? Now question number 4 is a word problem, which is an application-based problem, right? So this is different, a little bit different from the problems that we worked so far, because those were straightforward. They were not application-based problems, and they had given us the data we would need to perform the hypothesis test outright up front, right? Here, we first have to understand what this problem is about, and we have to extract the data that we need to perform the hypothesis test and then work through the steps. And as you will note that for this problem, they haven't laid out the steps for us like they had done previously. But by this time, you should be able to remember the steps we need to perform the hypothesis test and, complete the problem. So let's first read through this problem and try to understand what it is about. It says toxic mushrooms, so something to do with poisonous mushrooms. Cadmium, a heavy metal, is toxic to animals. Mushrooms are, however, able to absorb and accumulate cadmium at high concentrations. The Czech and Slovak governments have set a safety limit for cadmium in dry vegetables at 0.5 part per million or ppm. M. Melger et al. Measured the cadmium levels in a random sample of the edible mushrooms and published the results in a paper. Here are the data. So they've given us a set of data which represents the concentration of cadmium levels in a random sample of edible mushrooms. Now, the question is, at the 5% significance level, do the data provide sufficient evidence to conclude the mean cadmium level in mushrooms is greater than the government's recommended limit of 0.5 ppm? assume the population standard deviation of cadmium levels in mushroom is 0.37 ppm, and they've given us a hint or a note saying the sum of the data is 6.31 ppm. So what this problem is about is cadmium is an element mineral, an element found in soils, and when plants absorb the elements from the soil, and if they absorb cadmium, then if the concentration is above a certain level, then it can be toxic to whoever consumes the mushroom, right, the particular vegetable. So the governments of Czech and Slovak, they have specified a safety limit for the cadmium concentration as 0.5 ppm, right? And then researchers have performed a study on mushrooms and taken measurements of the concentration level of cadmium and come up with the data here. And what we are supposed to do is perform a hypothesis test to see whether mushrooms that grow in those countries perhaps have a concentration level higher than 0.5 or not. All right. So the first thing we must do is gather the data. All right. We have to gather the data. Now, as you can see over here, again, you may need to read these application-based problems a few times. Not once may not be adequate, right? So here I have to first determine what kind of test procedure we are going to use. As we see here in the last sentence, it says, assume the population standard deviation of cadmium levels is 0.37 ppm. So we know here that the population standard deviation is known, right? So the population standard deviation is given, so sigma, right? That's what the population standard deviation is, sigma. That is known, that is given to us, so we can perform this test using the z-test procedure, right? Now, the z-test procedure formula for the test statistic is z sub 0 equals x bar minus mu over sigma divided by square root over n, correct? Now, we do need all this data, the x bar, the mu, the sigma, and n, in order to come up with the test statistic value. Additionally, we also need to find the significance level and so on. All right. So let's search for these pieces of information in this problem. What would x bar be? Okay. So just give me a minute here. Okay. So we are, at this point, we are gathering our data. X bar. Now, they haven't given us x bar explicitly. However, they've given us the data, and we know that the formula to find the mean, x bar is the sample mean, correct? So the formula to find x bar is sigma x divided by n, right? So all we can do is we can add up, sum up all this data and divide it by the number of data given to us. So we have n equals 12. So sigma x. Now they have given us over here in the last line, it says the sum of the data is 6.31 ppm. So we need not go and start adding up this data since they've given us the information. It's 6.31 and n is 12. So x bar will have a value of 0.525. All right, when you perform this division, you should come up with a value of 0.525. Now, n, we know we will need that in our equation for the test statistic n is 12. And we've already used that value when finding the sample mean. And then we have sigma is given to us as 0.37 ppm. So sigma equals 0.37 ppm. All right. So we have to figure out what mu is. Now this mu is the null hypothesis mu, the null hypothesis mean. So we have to figure out what the null hypothesis mean is. So what would that be? For here, I'm going to write mu equals, it is the safety limit set by the government. That is the established mean. All right, that the safety limit is 0.5 ppm for dry vegetables. All right, so mu is, this is what the null hypothesis mu is. So I'm going to say mu sub 0 is 0.5 ppm. All right, whatever they have set as the safety limit. So we got all our data that we need to find the test statistic, right? Now, what we need to do now is come up with an alpha, which is the significance level. Significance level, alpha. Now, significance level is 5%, all right? It's 5%. But alpha is the decimal counterpart of 5%. So 5 divided by 100 is 0.05. So that's going to be our significance level that we are going to use to perform this test. Now, we can start our steps at this point. Step 1 is state your hypothesis. State hypothesis. That's the first step in any hypothesis test. And we have to state two hypotheses. One is the null hypothesis. The null hypothesis will say mu equals, null hypothesis always have to have a equal sign in it. And you always have to state your null hypothesis using the population notation. All right. Mu equals 0.5. That's our null hypothesis, what we wrote down here. The alternate hypothesis is also going to have a mu, and it's also going to have the 0.5 on the other side, but the sign that's going to, the symbol or the sign that it's going to have in between mu and 0.5 has to be determined from the wording here. So I'm going to read, at the 5% significance level, do the data provide sufficient evidence to conclude the mean cadmium level in mushrooms is greater than the government's recommended limit? So we have to use the greater than sign for the alternate hypothesis. All right, so that's how you can extract the alternate hypothesis statement. You do have to get it from the wording of the question. All right. So alternate hypothesis states mu greater than 0.5. So what kind of tail test would this be? When it's greater than, when the alternate hypothesis is greater than, it's going to be a right tail test. A right tail test, right? Good. So that's step 1. That completes step 1. Step 2 was to come up with the significance level. So significance level is given to us. It's nothing that we have to think about. Significance level alpha equals 0.05. That's all. All right, just state it. And then step 3 is to find the test statistics, and that is your evidence. All right, the evidence comes from the data that's of our sample study. So find the test statistic. That's the next step, step 3. And we will use our formula. Again, we already determine that it's going to be a z-test procedure because the population standard deviation is known. Let's write the formula first for the test statistic. We denote the test statistic as z sub 0, and the formula for that is x bar minus mu over sigma divided by square root over n, correct? So x bar this is our x bar 0.525. Now you have to show that you have plugged in the values correctly. And then mu is this null hypothesis mean, all right? So that's 0.5 divided by sigma is 0.37, so 0.37 divided by square root over n is 12. So now we can use our calculators to to calculate this. So we will end up with the numerator is 0.0258 over 0.37 divided by square root over 12 should give you 0.1068, and when you do this division you should get a value of 0.2416 roughly. All right, it's 0.24157 to the 5th decimal place, but we'll just round it up to the 4th decimal place. So that's our z sub 0, our test statistic, our evidence. Now that we have found a value for the test statistic, we can go on to our next step, which is step 4, where we use one of the, both the approaches to come up with a decision. All right, the first one is called the critical value approach, or the CV approach, where we find the cutoff point between rejecting a null hypothesis and not rejecting a null hypothesis. So let's start with a diagram. Always start with a diagram. So here we have our normal curve, and at the center of the curve is the null hypothesis mean, and its z value is 0, correct? And then because it's a right tail test, our reject region is going to fall on the right hand side of the curve. So the right end of the curve is going to be reject, and then the left hand side is going to be the do not reject region. Okay, and this is the area corresponding to the reject region under the curve. All right, and this area is what alpha is. Alpha equals 0.05. All right, that's comes from the significance level, right? So alpha is 0.05. The cutoff point is really a z value. The critical value is a z value whose area, in this case to the right, is 0.05. So what we are looking for is z of 0.05. Now, it's going to be a positive z value because it's situated to the right of 0. And that value is 1.645. Now, I have that memorized by now, but you have to look up your table or use your calculators. Let me look up the table here. The special table for the special alpha values shows that z of 0.05 is 1.645. That's how we got the values, or we get the values. So going back over here, our critical value, the cutoff point is 1.645. Now that we have identified that cutoff point, the critical value, we have to bring our test statistics, our evidence, and see in which region it falls on the curve. Does it fall on the reject region or on the do not reject region? So you can just show it on the curve itself. 0.2416 is going to be slightly to the right of the 0 mark, correct? So somewhere here maybe is 0.2416, and we see that falls in the do not reject region, correct? However, you have to write out your explanation behind taking the decision. So we have to state here first the critical value, the CV, is Z of 0.05, which is 1.645. And then we have to say that the test statistic of the Z sub 0 of 0.2416 is a value less than 1.645, and it falls in the do not reject region, Therefore, the decision, do not reject region. So in step 5, where we state the decision, in step 5, the decision is going to be do not reject. Do not reject null hypothesis. However, we also have to show the p-value approach. So here we have the p-value approach, because you have to find out or come to a decision using both approaches. All right. So what do we do for the p-value approach? We start with our evidence, our test statistic. So what we do is we take our test statistic value and find the area to the right. So find area to the right of Z sub 0 equals 0.2416, which is the test statistic or Z sub 0 value, test statistic value. Now, why do we find the area to the right? Because it is a right tail test. So the tail type of the test determines whether we find the area to the right or whether we find the area to the left for the p-value approach. All right. So I'm just going to draw a quick figure here, a simple one. All right. So 0.2416, we said, is located a little bit to the right of the 0 mark. So what we are interested in is all this area to the right. This area will be our p-value. It will be our p-value. So if we look up the table, all right, we will come up with a p-value of, well, the area, the p-value in this case is the area to the right of Z sub 0 equals 0.2416 is 0.40455. All right, so 0.04 or 0.05. So, oops, excuse me. So I'm going to draw a quick figure here for the p-value approach. This is not the pen I want to use. Okay, so it's still going to be the normal curve, and if 0.2416 is located slightly to the right of 0, then extend a vertical line up to the curve and all this area to the right will represent our p-value. All right, so it is the area to the right of 0.2416. Again, you have to refer back to your Z table. All right, let me see if I can pull up the Z table, which is here, but this time you have to go back to the full table. Okay, so 0.2416 will be its positive value. 0.2416 will be 241 something, 0.5948, but this is area to the left. So when you go back here, you have to do 1 minus whatever value you obtained from the table, and the corresponding p value to the right, the area to the right, will be this. P value is 0.4045 roughly. Okay, that's the p value. Now in the next step, what you do is you compare p with alpha. Compare p with alpha, and the question is p less than alpha? All right, here we see that p, all right, here 0.404 is way higher than, all right, it's greater than the alpha value 0.05, and if p is greater than alpha, then your decision should be do not reject, which agrees with what we got using the critical value approach. So our step 5, our decision was do not reject null hypothesis, and then the final step is to interpret, is the interpretation. So we are going to say that at the 5% significance level, now because we did not reject, we have to say the data do not provide sufficient evidence. All right, do not provide sufficient evidence to conclude. Now you have to state this interpretation in context of this particular application-based problem. So it do not provide sufficient evidence to conclude. Now, what I suggest is just take the wording from the question itself. To conclude, everything that comes after to conclude, the mean cadmium level in mushrooms is greater than the government's recommended limit of 0.5 ppm. So you can just use the same wording as the question. That way you do not have to think how to phrase this. All right, just pick the wording from the question. Do not provide sufficient evidence to conclude that the mean cadmium level in mushrooms, is greater than the government's level of limit of 0.5 ppm. All right, you do have to state the interpretation in context of your word problem. Okay.